This is Astronomy Daily Live for the 14th of July, 2015. It's incredible that it's the 14th of July already. That's pretty amazing. Yeah, it's been a pretty fast year so far. Pretty fast. Yeah, yeah, it's gone by pretty fast. So, don't know if that's a good thing or not, but come on in. I'm going to get this so my Linux machine doesn't freeze. I've got the chat open. Atawahinta is there. Well, Ata, it is 2 hours UTC on the 14th of July. UTC. So, depending on where you are on the planet, right, you're going to, possibly have a different, um, local time. Local time. I see that Bobby has popped in. I'm going to put my headphones on here, and I'm going to turn you down. Let me see if I can turn you down. I don't think it remembers. Okay, I got to turn you down. There we go. How's everything over there, Bobby?
Having some trouble.
Having some trouble? Yeah. Okay. Well, do what you got to do. Yeah, it's not really being picky, Atta. It's um, sticking to what we call universal time. Coordinated universal time, and that time is right now, and we because of how we measure time. Um, it just uh, there needs to be some kind of starting point, right? Some kind of reference. It's like, okay, uh, this particular place, we're going to offset from that, and so yeah, and that's how these live streams are dated. Um, so you'll always see, uh, you know, like when I create a new event for tomorrow, I will put the 15th. uh, the 15th, because that'll be 2 hours UTC on the 15th, right? All right, well, cheers. Get everything worked out, Bobby?
Yeah, everything's working out well now.
Cool. Very, very cool. So, yeah, I was, I've been a little, a little lazy in terms of research lately, and so I was thinking about the at least a couple of the projects that I was working on and just sort of stopped working on for I don't know the past I don't know month or so. Just it's just like oh I don't want to work on that. I don't want to work on that. Hello, puppy.
Hey, this is Blackie, by the way.
Is he just a baby?
He's about 2.5.
2.5 years?
Yeah.
Oh wow, okay. That's awesome. What's his name? Blackie?
Yes, he's half Chula Russell.
Very cool. Very cool. Yeah, all we have around here are mutts too. So,
Also got 2 dachshunds too.
oh my gosh.
Mm.
Yeah, we've got a min pin. Yeah, he's pretty intense. So, anyway, so yeah, I I started thinking about a couple of the projects that I was working on, and I think I think one of the ones that I think I really want to try to finish was this one that I was working on. Oh, cheers!
Yeah, I got me some water as well. Whoa! Oh,
Whoa!
buddy. Mm.
So,
So,
and I don't remember when I stopped working on this, but I guess it was sometime late last year because yeah, I don't know if I worked on it this year or the end of last year. But there's this there's this project to try to uh, uh, detect and then characterize asteroids. Right? There's a actually one of the main ones, um, Catalina Sky Survey, uh, is just to the west of me, um, just north of Tucson. So they are scanning the sky every clear night and um, looking for new things, new asteroids mainly. But they find comets and supernovae and all kinds of transient stuff. But I mean, there are limitations to what they're doing. I mean, basically, they're doing what has been done for over 100 years now, and that is take two pictures of the same place in the sky, separated by some time, and then look at the difference between them and see if anything has changed. And so that's a really old technique that that works. It works really well, but um, there there are some problems with it, um, and that's sort of where I came in. Is that I thought, and I'm sort of giving the end of the story at the beginning. I thought that uh, my idea would work to solve this or these problems, and it turns out that it doesn't work. It doesn't work. Uh, there's a there's a big problem that it just uh, it makes it way too expensive. But anyway, so So what I did is I started writing a paper on this. So I just wanted to show you because it's kind of interesting. The analysis was kind of interesting. I'm going to hide that and I'm going to go back over here. Now this is just a, I mean, it's not even a draft, right? It's like a really, really moderately roughly written uh, outline. So don't read this as if it's like a finished thing. These are just, this was basically just a brain dump over the course of a couple days, um, because I thought that I was onto something, and yeah, it turns out that I'm not. So the fundamental flaw with how they are looking for asteroids today is that um, all of these systems require the asteroid to be bright enough to see, and uh, well, there are problems with that. Um, and it really, it sort of doesn't really matter how large of a telescope you get on this. Um, uh, you're still going to have lots of limitations because you're 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 um, counting on reflected light, and that is uh, that can only get you so far, right? So the brightness of an object, the apparent brightness of an object depends on three things, right? The size of the object, the distance the object is to the observer, and the reflectance. So, how much light is actually reflected from this thing. Um, and yeah, uh, detectability then depends on the size of your scope, um, the sensitivity of your instrumentation, how good your calibrations are, and how well your system of detection is. And so most asteroids are detected near opposition because they're the closest to us, and so they're the brightest they're going to be. And so yeah, there's no way to see these things when they're very far away because they're just too faint to see. And so my thought was, it's like, okay, why don't we use stellar occultations instead? So, if there's a sufficient number of asteroids out there, um, given a distribution of stars in the sky, those asteroids are going to um, 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 occult those stars um, probably pretty often. And yeah, it's kind of interesting because even um, given a, let's see, Occult 4 is a piece of software that allows you uh, to predict asteroidal occultations. Maybe I should show you Occult 4. Let's see if we can find it here. If you want to start observing asteroidal occultations, Occult 4 is a necessity because it will tell you you know, down to the second uh, when an occultation is going to be visible from your location. And the interesting thing is you know, any particular location is going to have, on average, about one or so. Now, it's not exactly one per month. You might go a few. So, yeah. So, I mean, it's not distributed. Why isn't this coming up here? Why isn't this coming up? But Bobby, where was I going to go? Do you remember?
I forgot. I forgot too.
Oh, I hate that. I hate that. A sip of water and just completely washed it out of my head. Oh well. I'll uh I'll try to remember. Um oh, that's right. Occult. We wanted to go see Occult 4. And it sounds, like some kind of horror flick or something. It's probably one of the worst named pieces of software I've ever seen. But there you have it. So Occult version 4.5.5. This is where you get it. This is where you get it. You have to do a little installation procedure, and then you have to set it all up. So that requires downloading some large files. It knows where to go to find all these files. You just have to tell it to go get it. So the setup is a little tricky, but once you set it up, once you have a catalog of asteroids and uh, nice dense star catalog, uh, you can run this and have it tell you over a certain time period what occultations you're going to be able to see from your location. And yeah, I think it works out to be about maybe one a month or so, which is pretty often. You know, it's not bad. You know, if uh, if you had 1,000 observers um, spread over the world or spread over the country, uh, each of them seeing one occultation a month, that's 1,000 occultations a month. That's not bad. So yeah, yeah. So that was the basic idea, was to see if we could set up a system to detect these occultations. And the cool thing about an occultation uh, is that it doesn't matter how bright the asteroid is. It doesn't matter. Um, what matters more is like size and distance to us. All right, so I haven't thought a lot about this in a long time, so I'm probably missing a lot of interesting points. But um, point is that at least what I thought, right, is that this occultation system has a lot of advantages, right? You can use a small telescope. It doesn't have to be really, really big. Um, it probably would have to be image intensified, So that's just um, it's a technology that just um, intensifies images uh, by a certain factor, and so that just allows us to see fainter things, um, and the possibility of actually detecting asteroids less than 100 meters across, which no one can do at this point, or at least very very rarely. If I think the only objects that they have detected that were like less than 100 meters across were ones that actually hit the Earth, because they detected it like hours before it hit the Earth. So they're they're just not able to see things that small from that far away. So yeah, but this I thought had the possibility of doing that, and so yeah, then I just sort of went into what occultations are, and yeah, so of course, in order for occultations to take place at all, there also needs to be a sufficient number of stars in the sky for asteroids to occult. Um, and there needs to be a sufficient number of asteroids to do the occultation. Um, so yeah, it turns out that um, let's see, where's my table? Probably way at the end here.
So we are just trying to find any visible objects that could hit the Earth, right?
Yeah, there's sort of um, two two primary goals. I I think the first goal uh, is to try to detect as many um, near Earth objects that we possibly can. So down to as small as we possibly can. So and near Earth objects are objects. Well, I mean, hence the name, but
Yeah.
they're objects that can come very very near the Earth. Their orbits are such that they're actually either very very near the orbit of the Earth, or uh, they have intersection points where our orbit and their orbit cross. So yeah, it's uh, these kinds of things happen from time to time, and it's not a matter of if, it's just a matter of when. And the whole idea is that uh, if say ideally, right? Say ideally here. I'm going to go back to me because this is a this is a good conversation here. Um, uh, so
So
how
it's your idea about how soon they will know when there's going to be an object that's probably going to hit the Earth.
Yeah, so that's the whole point, is to try to detect these things as early as we possibly can. So if we can do anything at all, we can do it, right? Either you know go out there and deflect it, or blow it up, or I guess those are the only two options. Uh,
What kind of defense technologies we're going to be looking at to defend ourselves against asteroids?
Nuclear. It's the only way. It's the only way. I mean, if you have a mountain moving towards you that is going to hit pretty much anywhere would be a disaster, right? If it hits in the ocean, which there's a 70% chance it's going to hit the ocean, that's a pretty good chance, right? I mean,
So even if it hits the ocean, it's still going to wash us out, right?
it's going to be nasty. I mean, it depends on the size, and it depends on how fast it's going. Lots of things, but typically, uh, yeah, something pretty big is is going to be pretty nasty. So the whole idea is, let's try to find them um, uh, when a likely collision is like 100 years in the future. Um, Now, I don't think that we can do that yet. Um, as I say, and it's absolutely true. It's absolutely true. In order to uh, determine orbits of objects, like an asteroid, doesn't matter what it is, right? But in order to determine the orbit of these objects, you most definitely need to be able to measure their positions very, very precisely, right? That's fine. But the other thing that is absolutely critical, right, is time. You need a long period of time. So you can make 1,000 observations in one night and think that the number of observations is going to allow you to figure out its orbit. It doesn't work like that. That thing has to be able to move a little bit. So what you have to do is you have to be super patient and be like, okay, there's one. Let's look at that one every single month, right? Or every other month, every 6 months, whatever. You know, um, get it on some kind of schedule. Cheers. And give it. You're going to have to give it 5 years or so. Um, see what it does, right? Um, so that's what you need in order to determine a good orbit. So being able to predict the position of an object 100 years in advance with any kind of precision at all, your orbit has to be really, really, really good, right? And the only way to get that uh, is a long period of observations. Um, you can observe this as much as you want. That's fine, right? But you're going to have to do it for 5 years.
And can it be done with space telescopes, or what's the better detection method?
Yeah, no, I mean once these objects are known to exist, right? It's like once they're found, once they're discovered, um, uh, then uh, everybody else can know where to find it. And so that's where you get these groups to make these observations over the course of a few years, and really refine that orbit. Um, so yeah, a lot of what you hear about asteroids possibly hitting 20 years from now, 30 years from now. Yeah, I don't know if our orbits are good enough to do that. I sort of doubt it. So this what I am doing in this paper, which I'll get back to, was I'm not necessarily wanting to use this system for follow-up observations. I I sort of saw this as just a detection system, right? I mean, it's going to see known asteroids and unknown asteroids because all of them are going to occult stars. Anyway, there are 1.1 billion stars down to magnitude 17. So that's quite a few. 1.1 billion, is that right? Yep. 1.1 billion. So if you sort of spread that number over the entire sky, then you'll sort of get an average number of stars per square degree. And so if you can see down to 17th magnitude, there will be 26,784 stars per square degree. The square degree is about 4 times the area of the full moon, right? So in that small space, on average, you'll see like 27,000 stars down to magnitude 17. Now that's going to vary quite a bit, right, in the real sky, because in the real sky we have the Milky Way, which is a large concentration of stars. It's the disk of our galaxy. So there's going to be a lot more than 27,000 stars per square degree in those areas. And outside of those areas, there is likely going to be less than that, right? So this is just an average. If we sort of evenly spread those 1.1 billion stars over the entire sky, each square degree would have 26,784 stars in them. So that's quite a few stars, right? That's quite a few.
So if we get to that level 17, we should have a better chance, right?
Well, that was my thought, because the more, I mean, there are 2 requirements, right? I think I listed these. Where did I list those?
And our Astro's got a great idea about using warheads against asteroids.
Yeah. I'm I'm sort of wondering if just regular bombs aren't quite enough. I mean, I'm sort of thinking that what an awesome use of that kind of device, right? I mean, think of the irony there, right? The irony is that this device that was going to destroy us is now going to save us. I think it's great. I think we should use nukes on them. And what a great view. I mean, that would be awesome, right? To see like 100 megaton bomb explode in space. Wouldn't that be cool? I think so. Man, I'd watch that. That'd be great. Blow this thing up to smithereens. The only problem really, with blowing things up is that, you still have to deal with this shower of smaller pieces. And that might actually be worse. So yeah.
Yeah, Uncle Bill Durham was talking about the RC boat. I was wondering if they're gonna like rebuild it since Maria struck it all the way down.
Uh, radar capability good to Jupiter. Very cool. Yeah, Arecibo is absolutely fantastic. You know, they use it as like this radar thing, and I don't know if you all saw um, the binary um, asteroid that they took a picture of, a radar image of. Very very cool. It's like a binary asteroid. It's awesome.
Now they're planning on rebuilding the RC boat because of Maria.
Yeah, I guess it along with the rest of the island was just like devastated, right? Just absolutely destroyed. And but they got operational pretty quick. I uh, I don't think that there was like a huge amount of damage. So it was apparently easy to fix, and they were back online, and I don't know, a few months afterwards.
Yeah, that's
So
what Art Instra was talking about.
yeah. Yeah, that's absolutely amazing. They they keep well, I keep hearing stories, right, about, it's closing, it's closing, it's closing. And, I hear a story about, yep, it's going to close now. And then, like 2 days later, I see this, radar image of these asteroids, and it's like, well, what? I thought they were closed. So, yeah, nobody wants Arecibo to close. I don't really understand what is going on there. It seems I mean, to me it's sort of a no brainer that Arecibo should not only be there and running and everything else, but contributing to the local economy and everything else. It's got to be great, you know. So yeah, I don't know. I don't exactly know what the problem is, and it's like, okay, well, you close it. I mean, you're just going to leave it there, right? So I mean, you're just going to mothball uh, this huge radio dish. I mean, come on. So yeah, I mean, if it's being privately funded, that's great. It just needs to keep running. I mean, come on, it's awesome. No, Bob Dog, you're exactly right. It's a cost. I mean, it is, it's overhead. Yeah, it's just not, um, and that, that was not an intended pun, but it actually is. It's overhead. Stargazing is overhead when it comes to making money, right? So it's not it's going to consume for sure. Yeah.
I think one of the Arcibo, what they did one time is they have a shortwave event at the Arcibo Institute,
Hmm.
and they were. I think it was pretty darn awesome. I caught it like I forgot where at, but it's pretty darn cool. They even had an SSTV image at late at night and stuff. That was pretty darn good too.
Huh. SSCB, you say?
SSTV, Source
SST.
TV.
Yeah. Yeah. Okay. I got you. Yeah. Cool. Cool. So, I mean, that's something that you can hear from your location, or do you have to go there?
I can hear from my location.
Yeah. Okay. Yeah, because you're pretty well. I mean, well, closer than I am, but still, that's probably pretty far. Yeah.
I kind of may agree with that.
Okay. All right. Well, cool. Let's keep going with this. So that was the whole idea. That it's like, okay, let's see if we can detect occultations. Well, um, turns out that a an object that is 100 meters in diameter, moving at a relative velocity to Earth of 30 kilometers a second, takes what is that? 3.3 thousandths of a second to move one of its diameters, right? So, and that's how long the occultation would actually last, right? Is less. Well, what is that? 1/3 of a hundredth of a second. So that's really really fast. Uh, that is so fast that I think at this time there is no way that we can detect those things. So under normal circumstances, uh, uh, yes, the occultations are occurring, but they're happening so fast that we don't really even know. Um, so so we're not going to be able to detect those because they're just too fast. But sometimes the relative positions, and I'm sort of reading here, between the location on the Earth and an object. Um, yeah, um, there are going to be some fairly regular times when the distance, the apparent size, and velocity um, sort of conspire to create this slow event, and that usually happens. Um, uh, you'll see this often. Some object is stationary, uh, which means it isn't moving in the sky, right? Uh, uh, it looks as though it isn't moving at all, and that's caused by the relative motion of the Earth and that object. Um, if the object is further from the sun than us, then uh, we're moving faster than it is, and from time to time we're going to catch up to it and pass it. And it's sort of during these times where you can get these events, which I call slow events, uh, um, which is when these objects are near stationary. So what I do is I go through this and I calculate, how many slow events should there be. Uh, I forget per square degree per year, I think is what I did. Um, so, so there's that, and then I have to also calculate um, um, the oh, oh the probability that a star um, is going to be in the location of this slow event, right? Um, because both of those two things have to occur at exactly the same time. We have to have an occultation long enough that we can actually detect. And the asteroid obviously has to be blocking a star while it's moving that slow. So those were those two probabilities, and it worked out, to just be probabilities. And I could take into account, the number of stars. I had a range of number of asteroids from 10 million up to 10 billion. We really don't know how many small asteroids there are, but I tried to find a couple of references, and yeah, the range was pretty wide, right, by a factor of 1,000. So nobody really knows how many 10-meter objects there are. There could be quite a few of them. So then I divided it up into different slow event occultation durations. So tenth of a second, quarter of a second, half a second occultation lengths. At least a tenth of a second, right? And at least a quarter of a second. It could be longer. And so so if there are 10 million asteroids, right, 10 million total, then you will see from a particular location about 4 per year per square degree. If you're looking for a tenth of a second occultation length or longer. So that's not great. But as you can see, as you increase the number of asteroids, the number of occultations obviously goes up in exactly the same way. So if you have 10 billion asteroids, then you're going to be able to see, 4,369 occultations per year per square degree that are a tenth of a second or longer in duration. So that's pretty extraordinary, right? I mean, if you can, that's per square degree. So if you have a telescope that can see 10 square degrees, right, then you can multiply this by 10 and know that you'll be able to detect 43,000 occultations per year. And that's a lot. that's a huge number, right? So this was all very, very exciting. And I was working on it, and then I realized this, that the analysis that I did, actually the software I used, right, Occult 4. I'll come back to me for a minute.
So you can use it even on the cheapest telescopes, or what?
Well, yeah, the idea was that we really needed to see down to about 17th magnitude for a like a 50 millisecond exposure, 0.05 second exposure. And the only way to do that with a pretty small scope, like the scope I've got, is with these image intensifiers, which can intensify the image by a factor of 1,000, which means a 17th magnitude star would actually look like like a magnitude 9.5 star, and my telescope can definitely see a 9.5, easy, easy. So yeah, the idea was to use use small scopes with image intensifiers um, to be able to see down to about 17th magnitude or so. So
Is
that's
it better telescopes or binoculars will be good too?
um, you really need a telescope. You need the aperture. You need the size. You really binoculars aren't going to get you down to 17th magnitude. Not a chance. Not a chance. So yeah, you need you probably need at least hmm, yeah, really at least an 8 inch, at least an 8 inch, 20 centimeter. Yeah, yeah. Because otherwise, yeah, it's going to get a lot harder. Yeah. So yeah, you know, um, our instro. What I did in this very rough draft, almost thinking out loud, um, just write stuff down, kind of thing. Uh, um, I I sort of envisioned an even distribution, right? Which is completely unrealistic, right? The distribution of stars in the sky is like the furthest from even that there can possibly be. It's very organized, right? Um, and same goes with the asteroids. We can probably guess that most of the asteroids are going to be along um, the ecliptic. Um, Not all of them will be, but a lot of them will be for sure, especially a lot of the small ones. So yeah, what I was doing here was just sort of a preliminary thing where you know made an assumption that there's an even distribution of stars and asteroids, which is it's 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 ballparky. Yeah, it's it, it gives you, I think I think it gives me at least sort of a rough idea of what I'm dealing with, right? And I can see my next thing, would definitely be to sort of be able to model or uh, put into this whole thing different kinds of distributions, um, because then I could really refine that. What I'm looking at here is sort of an average, right? So all these numbers you can sort of consider as averages, um, where depending on where you're looking in the sky, those numbers are going to be way high or way low. So yeah, I don't know. I don't know what that range is. I have absolutely no idea what the range is at all. But I definitely know what the average is, and so that was really great. But what kills it? What kills it is that um, so using Occult 4, okay, this occultation prediction software. What it does is um, you can tell it to to show you all occultations where the asteroid gets to within a certain distance of the star, right? So maybe not exactly occulting, but just a little bit off, right? And wow, I'm thinking about that now, and it's like, huh, I wonder. Anyway, so the problem is that even this software isn't good enough to be able to perfectly exactly pinpoint the fact that that occultation is going to go over you, right? And the problem um, becomes obvious if you have a, let's just say, okay, let's just say a basketball sized asteroid, right, a foot across, right? It's going to occult a star, right? And you're going to be able to see that occultation. What that actually is, right? What that actually is, what you're experiencing is the shadow of that asteroid being cast on you, right? So the starlight is coming in, it's hitting the asteroid. The asteroid is exactly right in between you and that star. So what you actually see is the shadow. So now I think that you can imagine that, as this asteroid moves, the shadow is actually moving across the ground, right? Well, if it's only a foot across, then if you're a foot away from that center, you're going to miss it, right? So you can sort of extend that now and say, use a footprint of like 100 meters or 10 meters, whatever size you want. Um, the problem is that uh, in detecting these smaller objects, especially the smaller ones, if you're not exactly right in that path to very high precision, right? I mean, you've got to be, for a 10-meter object, if you want to be able to detect a 10-meter object, then you have to be um, within a 5-meter radius of the center of that thing, or you're not going to see it. So that's really hard. That's really, really hard. And that's what stops my show is that it turns out that it's absolutely true that there are lots and lots and lots and lots and lots of occultations going on, but the 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 probability that you're going to see a small asteroid go in front of a star is, well, suffice it to say, that's where I stopped because I realized it's like, this is not going to work. So what I have to do now is I actually have to go through those calculations um, because I do want to finalize this because I think it's an interesting, I mean, even though, my goal was to show that it was going to work, right? And it turns out that it's not. It's just not. Um, if we can eventually do shorter exposure times, then maybe something like this would work. But using current technology, it's just not feasible yet. um, but here, I want to show you these really cool plots that I made. Um, and I actually made some movies too, which I should post somewhere. I can put them on here on this YouTube channel. So here, but let me show you these plots because these plots are pretty interesting. I'm going to hide that. So I was going through, I had all kinds of ideas. It's like, if if I can do this, then it's like, okay, then I can do this and this and this and this and this. it was going to be great. Well, let me shrink this down. Microsoft Viewer. How do I shrink this down? Huh. Let me open this again.
How crucial is the timing that you got to have?
Very crucial. Very crucial. Yeah. I mean, you're looking for uh, a 1/10 of a second occultation event. So yeah, you've got to be well, one, you've got to be able to sample at least twice as fast as that. Well, I don't see how I can zoom. It's up here somewhere. Yeah, here we go. 75%. There we go. Let's see what that does. So yeah, pretty crucial, I would say. Okay. These you're going to be able to see. So here's 4 plots, right? And I hope that you can here, can I 80%? Let's see what that does. That's okay, isn't it? Yeah. So along the x-axis here is time, right? So this is a 10-year time span from the 1st of January 2017 to the 1st of January 2027. So this is 10 years here. And these 4 plots are showing 4 different things about this particular asteroid. Now I'm going to try to okay. Now I know what I need to do. Okay. So this first one up here is distance in astronomical units between us, the observer, and this object. And this is just a randomly chosen asteroid. It turns out to be asteroid number 503997. And let's see, we can zoom. Let's see what happens when we zoom in like 200. Ooh, you can start seeing the numbers there, I think. I hope. So you can see that the distance between us and this asteroid varies actually quite a bit, right? I don't know if you can read those or not, but this lower one down here is almost 1 AU. There's a 1 right there. So it's almost 1 astronomical unit at its closest. And furthest away, it gets out to almost 4.5 astronomical units. So that's quite a distance, right? Of course, 1 astronomical unit is the distance between the Earth and the Sun. So that's a huge variation, right, in distance. And the reason why it's wiggly like this, these wiggles here are due to the motion of the Earth, right? This object is further away from the sun than the Earth, so it's moving slower than the Earth. So every year, the Earth is going to get closer to it, and then further away, and then the next year it's going to get close again, further away. So as you can see, there should be about 10 of these across. 1, 2, 3, 4, 5, 6, 7, 8. There's 8. Well, there's 1, 2, 3, 4, 5. 6, 7, 8, 9. Yeah, it actually does work out to 10 years. So yeah, that's what these sort of high frequency wiggles are. These lower frequency wiggles, you see how this low is really low and then it goes up higher, stays the same, goes down again. So this is sort of a lower frequency thing. That has to do with the motion of the asteroid, right? And it sort of looks like it might have like a 5-year um, orbital period, right? Because it sort of, well, I guess it starts at a high, so maybe like a 4.5-year um, orbital period around the sun, something like that. So this next one is, what is it? The apparent size in micro arc seconds. So let's see if I can. So a micro arc second, does that compute? So uh, the full moon is about 1/2 of a degree uh, um, across. So if you were to sort of put together 4 full moons in a little box, right, a little square box, that would be 1 square degree. Okay, so take that one side, which is just a degree. In 1 degree is 60 arc minutes, and each arc minute is divided into 60 arc seconds. So 1 degree is 3,600 arc seconds. So you follow me? Okay. Cheers. So a milliarc second is 1,000th of an arc second. And a micro arc second is 1 millionth of an arc second. So these units here that I'm showing you now on the right on a logarithmic scale, these are in micro arc seconds. So 100 micro arc seconds is 1/10 of a milliarc second, right? 1,000 micro arc seconds is 1 milliarc second. So this is the apparent size of the asteroid. And as you can see, oh man, I didn't mean to do that. I wanted to show you the distance plot and that at the same time. So as you can see, the apparent size of the asteroid gets bigger as it gets closer to us. Makes sense, right? So that's all that's showing is just the apparent size of these asteroids. This is assuming, I do have to say this, this is assuming an asteroid size of 100 meters. 100 meters. So as you can see, here it gets close to the Earth, not as close as here, so its size isn't as big as that. So I think that makes sense, yeah? But these are the actual, calculations. It's always nice to see numbers. So the next plot down is the apparent velocity. So this is how many micro arc seconds per second. Arc seconds per second, is that what it is? have to confirm that. Yeah, micro arc seconds per second. So that's what this is showing. So this is showing, you know, how fast it looks like it's moving in the sky. And so the lower this number is, right, the slower it's moving. And that's a good thing, right? Because we want a slow event. So if an occultation is going to occur, it's going to be long enough for us to detect. So as you can see, you know, there are times when it's moving relatively fast, and there's times that it's moving relatively slow. It's kind of interesting to you know, correlate these with distance and size and everything else. And it's like, you know, okay, it's starting to slow down, right? It's starting to slow down, and then it reaches this minimum, and then it speeds up, or it at least looks like it speeds up again, and then slows down again, and then speeds up again. So what's with these weird speed ups when its apparent size is large and its distance from us is really small? What's going on there? So those are the kinds of things you just got to think about a little bit. I'm not going to give you the answer today. So this last plot shows the 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 time that it takes in seconds for this asteroid to move one of its diameters. So that depends on its apparent size, right? Which is dependent on its distance. So I've made a red line here showing that is 1/10 of a second right there. So as you can see, this asteroid does have a couple of times, a few times, what, at least four events, if not more. Um, we'd have to count, you know, the number of days. Probably a few days where the occultation length would be more than 1/10 of a second. In fact, this one looks like it goes up to almost half a second. So that's a really slow occultation if there's a star there. Here's a couple other ones too. So yeah, you know, I didn't mean for this to go quite this long. I actually wanted to revisit M104 because I think we should. I, I think I sort of shortchanged M104, and I want to give it its due. It's yeah, I don't think I covered as much about M104 as I wanted to. So I'm gonna try. I'm gonna try to remember for tomorrow to talk about M104, you know, pretty much right away, because it's a pretty amazing object, and I just sort of barely skim the surface there. It's a pretty amazing object. I think we need to look at it a little bit more carefully. So, all right. Having said that, I see that I'm a little over time. So, hope you like that. That's just that's that's a project that I want to finish. Um, So, and I think I can. I just have to do a little bit more work. I need to clean it up. Um, but yeah, I'll try to post some videos too, because I made some showing how the object was moving in the sky. versus some of these plots, and it helps a lot, to see, okay, this is how it's moving, and so this is why the plot looks the way it does. Sometimes, I mean, I totally understand plots can be very, very confusing, especially if they're gone over fast. So, yeah. All right, I'm gonna get out of here for today. I think, Bobby, are you doing a rabbit?
Um, yeah, if you want, you want Steve Roach or Voice of Reporter of the Week?
Um, Surprise me.
Surprise you? Okay.
Yeah. So, let's see. How can I? Let me, Bobby. Let me. Are you in chat here? I thought I saw you in chat earlier. Yeah.
Yeah, I was telling you that I was having trouble and stuff.
You're gonna get the. You're gonna get the wrench. You have the wrench. So go ahead and post your rabbit link if you wish. Um,
Yeah, not a problem.
all right, I'm gonna get out of here for now. So uh, if Bobby's gonna rabbit Hearts of Space, he will invite you. And all right, so I'm gonna get out of here for now. So take care, everybody. Um, I will see you on the spin,
Yeah.
like just a little less than 23 hours from now. 22 hours and what is that? 13 minutes?
Yeah.
39 minutes. I don't know. I'm
Yeah.
out of here.
And try that link. You might have to copy and paste it as well.
Okay. Let me. Okay. Cool. 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 All right. Well, thanks everybody. Thanks for coming in, listening to my blathering again, and it's all about sharing astronomy, talking about the universe, um, and it's fun, to talk about projects that are sort of ongoing that I want to get back into, and this really helped me remember a lot of things. So yeah, yeah. Now I sort of know what I need to do in order to move forward. So thanks for watching that process. All right, take care, everybody. I will see you on the spin. Bye.